Hello champs! Welcome to 90 Plus My Tuition app. Let's take few balls in a bag and let's count how many balls are there in this bag. And you count it like 1, 2, 3 and so on. Wait, what are these? These are called counting numbers. These positive counting numbers up to infinity are called natural numbers and we denote it by capital N. Next, let's remove all the balls from this bag. Can you tell me how many balls are remaining in this bag? Yes, there are 0 balls. Now, natural numbers together with 0 are called whole numbers and we denote it by W. Next, students, can you tell me what are negative numbers? Yes, they are -1, -2, -3 and so on. Now, what do we call the collection of positive numbers, negative numbers along with 0? We call them as integers denoted by capital Z. Next, let's consider a cake. I'll divide this cake into 5 equal pieces and I am eating only 2 pieces out of 5. Then it is 2 by 5. What is this number? Is it a natural number? Is it an integer? Such numbers are called rational numbers denoted by Q. Then what is a rational number? Any number which can be denoted in the form P by Q where P and Q are integers and Q not equal to 0 are called rational numbers. Next, let's try to represent all these numbers on a number line. The numbers starting from 1 up to infinity are called natural numbers. These natural numbers including 0 are called whole numbers. And the numbers negative numbers, positive numbers along with 0 are called integers. Then where do we represent rational numbers? We represent rational numbers between two integers like 1 by 2 comes in between 0 and 1. Students, note that there are infinitely many natural numbers, infinitely many integers and there are infinitely many rational numbers between two integers. Let's discuss some examples. State whether the following statements are true or false. Justify your answer. And the first statement is, every whole number is a natural number. Students, tell me, is there any whole number that is not a natural number? What about 0? Since 0 is a whole number and not a natural number, we can say that the given statement is false. We have the second statement, every integer is a rational number. Students, let's take any integer p. We can write it as p by 1, which is in the form of a rational number. So, we can say that every integer is a rational number. So, the given statement is correct. So far, we have studied what are natural numbers, what are whole numbers, integers and rational numbers. Let's discuss few exercise problems. We have the first question. Write 6 rational numbers between 3 and 4. Students, since we are asked to find 6 rational numbers, let us add 1 to 6. So, we get 6 plus 1 is equal to 7. Now, take 3 and 4. Multiply and divide by 7 to both these 3 and 4. We get 21 by 7 and 28 by 7. Students, can you tell me the rational numbers that comes between 21 by 7 and 28 by 7? Yes, they are 22 by 7, 23 by 7, 24 by 7, 25 by 7, 26 by 7 and 27 by 7. Now, these are the required rational numbers between 3 and 4. Let's move on to our next question. We have the question, find 5 rational numbers between 3 by 5 and 4 by 5. Students, isn't this question very similar to our previous question? Then how will you solve it? Here it is. Observe that both these rationals have the same denominator 5. So let's add 1 to 5. We get 5 plus 1 is equal to 6. Now multiply both numerator and denominator of these rationals by 6. We get 3 by 5 into 6 by 6 and 4 by 5 into 6 by 6. So we get 18 by 30 and 24 by 30. Can you tell me the rational numbers that comes between 18 by 30 and 24 by 30? Yes, they are 19 by 30, 20 by 30, 21 by 30, 22 by 30, 23 by 30. So these are the required rational numbers between 3 by 5 and 4 by 5. Students, let's study another interesting concept, irrational numbers. You know what are rational numbers, but do you know what are irrational numbers? Those numbers which cannot be written in the form of p by q, where both p and q are integers and q not equal to 0 are called irrational numbers. Root 2, root 3, pi are the examples of irrational numbers. Just like natural numbers, integers, rationals, there are infinitely many irrational numbers. Students, now we know what are natural numbers, integers, rational numbers and irrational numbers. All these sets of numbers together forms a collection called real numbers, denoted by capital R. Let's discuss an example. Locate root 2 on the number line. Students, you know how to represent a rational number, integers on a number line. Do you think it's quite difficult to locate an irrational number on a number line? Don't worry, I will make it easy. Let's consider a square OABC with O coinciding with the 0 of the number line and each side of the square being 1 unit in length. Let's draw a line OB as the diagonal of the square which forms two right-angled triangles OAB and OCB. Now, you know what is a Pythagoras theorem, right? Let's apply Pythagoras theorem for the triangle OAB. We get OB is equal to square root of 1 square plus 1 square, which is equal to square root of 2. Using your compass with the center at O and radius as OB, draw an arc on the number line which coinciding at the point P. Now, this point P represents root 2 on the number line. Let's discuss some exercise problem. State whether the following statements are true or false. And we have the first statement, every irrational number is a real number. Students, before answering this question, recall that a real number comprises of all the natural numbers, integers, rationals and irrationals. So, every irrational number is also a real number. So, the given statement is true. Let's see the second statement. Given, every real number is an irrational number. Students, this statement is clearly false because there are many real numbers which are not irrational numbers. For example, the number 2. It is a real number, but this is not an irrational number. Let's see another question. Are the square roots of all positive integers irrational? If not, give an example of a number whose square root is irrational. Students, can you give me an example of a number whose square root is a rational number? Here it is, square root of 4, that is equal to 2, and we know that 2 is not an irrational number. Hence, we can say that the given statement is incorrect. Let's move to our next interesting concept, real number and their decimal expansion. In this section, we will look at the decimal expansion of a real number and see if we can use this expansion to distinguish between rationals and irrationals. Whenever a real number is converted into decimal number, we get terminating numbers and non-terminating numbers. And these non-terminating numbers further leads to recurring numbers and non-recurring numbers. Let's study each one of these with the help of examples. Let's consider 5 by 4. Now, let's divide 5 by 4. We get 4 into 1 is equal to 4 and the remainder is 1. Let's put a decimal point and make this 10. We have 4 into 2 is equal to 8 and the remainder is 2. Since we have the decimal point, let's make this 20. We have 4 into 5 is equal to 20. So the remainder is 0. So we have 5 by 4 is equal to 1.25. You can easily observe that the process terminates after certain steps. That means the remainder is becoming 0. Such numbers are called terminating numbers. Now consider 10 by 3. Let's divide 10 by 3. We get 3 into 3 is equal to 9 and the remainder is 1. Let's put a decimal point and make this 10. Now again 3 into 3 is equal to 9 and the remainder is 1. Students, you can observe that this process is not terminating, and also after the decimal point the numbers are repeating. So we have 10 by 3 is equal to 3.33 and so on. Such numbers are called non-terminating recurring numbers. Let's take another example. Consider root 2. We know that root 2 is equal to 1.41421356 and so on. Students, you can observe that the numbers after the decimal point are neither terminating nor repeating. Such numbers are called non-terminating, non-recurring numbers. Students, we know that the real numbers are distinguished as rationals and irrationals. Now, terminating and non-terminating repeating numbers forms rational numbers, while non-terminating non-recurring numbers forms irrational numbers. Let's discuss some exercise problem. We have the question, show that 3.142678 is a rational number. In other words, show that 3.142678 can be expressed as P by Q, where P and Q are integers and Q not equal to 0. Students, observe that there are 6 digits after the decimal point. So, let's multiply both numerator and denominator of 3.142678 by 1000000. So, we get 3.142678 is equal to 3142678 divided by 1000000, which is a rational number. Next, let's move to another question. We have show that the number 1.2727 and so on can be expressed in the form of P by Q, where P and Q are integers and Q not equal to 0. Student, let's take x is equal to 1.2727 and so on. Let's call this as equation 1. Observe that after the decimal point, only two numbers 2 and 7 are repeating. So, let's multiply equation 1 on both sides by 100. We get 100x is equal to 100 into 1.2727 and so on. We get 100x is equal to 127.2727 so on, which can be written as 100x is equal to 126 plus 1.2727 so on. From equation 1, we can write it as 100x is equal to 126 plus x, which can be written as 100x minus x is equal to 126. It implies 99x is equal to 126. So we get x is equal to 126 by 99, that is equal to 14 by 11. Now this is a rational number. Let's discuss some more examples. Write the following in decimal form and state what kind of decimal expansion it is. We have the first one, 36 by 100. Students, let's divide 36 by 100. We get 0.36. Observe that after the decimal point, only two numbers are there. They are 3 and 6. So we can clearly say that this is a terminating number. We have the second question, 1 by 11. Students, let's divide 1 by 11. We get 0.0909 and so on. We can write it as 0.09 bar. Students, observe that after decimal point, the numbers are not terminating. And also observe that the numbers 0 and 9 are repeating. So we can say that this fraction is non-terminating and recurring. Let's discuss another question. We have the question, write the number 0.6 bar in the form of p by q, where p and q are integers and q not equal to 0. Students, let's take x is equal to 0.6 bar. That means x is equal to 0.666 and so on. Let's call this as equation 1. Students, you can easily observe that after decimal point only one number is repeating, that is 6. So let's multiply equation 1 by 10 on both sides. We get 10x is equal to 10 into 0.666 and so on. We get 10x is equal to 6.666 so on. We can write it as 10x is equal to 6 plus 0.666 so on. By equation 1, we get 10x is equal to 6 plus x. We get 10x minus x is equal to 6. Solving for x, we get 9x is equal to 6. X becomes x is equal to 6 by 9 and that is equal to 2 by 3. Now we can observe that this is in the form of p by q, where p and q are integers and q not equal to 0. Let's move on to our next question. Write the number 0.001 bar as a rational number. Students, first let us take x is equal to 0.001 bar. That means x is equal to 0.001001 and so on. Observe that after decimal point, 3 numbers are repeating. So, let's multiply equation 1 by 1000 on both sides. We get 1000x is equal to 1000 into 0.001 and so on. We get 1000x is equal to 1.001001 so on. We can write this as 1000x is equal to 1 plus 0.001 and so on. Now by equation 1, we can write this as 1000x is equal to 1 plus x. So it becomes 1000x minus x is equal to 1. We get 999x is equal to 1. So solving for x, we get x is equal to 1 divided by 999. So this is a rational number. Let's move on to another question. We have the question, write any 3 numbers whose decimal expansion is non-terminating and non-recurring. Students, you can write any 3 numbers of your choice. I'll take 0.01, 001, 0001 and so on. And I'll take the next one 0.20, 200, 2000 and so on. And the last one 0.003, 0003 and so on. You can easily observe that the decimal expansion of these 3 numbers are not terminating and non-recurring. Let's move on to another question. Write 3 different irrational numbers between 5 by 7 and 9 by 11. Students, first let us write down the decimal expansion of 5 by 7 and 9 by 11. We have 5 by 7 is equal to 0.714285 bar. And we have 9 by 11 is equal to 0.81 bar. So, the required irrational numbers are 0.71, 0.72 and 0.73. Let's discuss another question. We have the question, state whether the following numbers are rational or irrational. And we have the first number, square root of 225. Students, can you tell me what is square root of 225? Yes, it is 15. And we can write 15 as 15 by 1. And we can clearly see that it is in the form of P by Q. So, it is a rational number. We have the second question. 1.10100100 and so on. Students, observe that after decimal points, the numbers are neither terminating nor recurring. So, we can clearly say that this number is irrational number.